So we're looking now at multiplying and dividing complex numbers. The first example here, you can see we've got multiplication by a scalar, and this is out of your textbook. I've just put this here so you can see that if you're multiplying by a scalar, I know in an earlier video I showed you that you're effectively stretching where that complex number is. So multiplying by a scalar that's bigger than 0, you stretch that complex number from being this long to being this long out here. Now the thing to be careful is if your scalar that you're multiplying by is less than 0, what that does is it turns your complex number around, it changes its quadrant. So if it's in quadrant 1, it will then end up over in quadrant 3. If it's in quadrant 4, it ends up over in quadrant 2, and so on. So the reason that I've put this here, just to, you can use these formulas, okay, for the arg, big arg. What I would suggest is that you just do a quick sketch, okay, of what you end up with, so you know what quadrant you're in, and then you know whether you have to be going around for the angle. Previously, for example, here with z, okay, you had to go negative to get that angle, but when you multiply by this scalar k, you end up over in this quadrant, so it's positive. So my advice would be do yourself a quick sketch so you can see if you have to go around this way for your big arg or that way. Okay, we're here really interested in multiplying and dividing complex numbers by other complex numbers, and everything we do here is in cis form. So remember that the cis form of a complex number, r cis theta, is r with the cos theta plus I sine theta, like that. Okay, that's the r cis form. So when we're dealing with all our complex numbers here, we've got two numbers, z1 and z2, and we just subscript the r's here, r1 and r2, so we don't get them confused. They're different moduluses for each complex number. Now there's a big proof in the textbook that you can have a look at, and I advise you to have a look, see if you can follow it through. But what that proof does is it shows you that when you're multiplying complex numbers in cis form, you can very easily do that by taking the moduluses and multiplying them together to get a number answer, keeping the cis, and then adding their respective angles together. So r1, r2, cis, theta 1 plus theta 2. So that's what you get when you multiply your angles together. Okay, a couple of useful properties that come out of that is that when you're multiplying args, you're effectively adding them together. Okay, and then when you're multiplying moduluses, you're effectively just taking the two moduluses and multiplying them straight together. Okay. The other thing that's interesting here is if you take z, which we'll just call r cis theta, if you multiply z by itself, what you're going to get is you're going to get r cis theta times r cis theta, and using the formula here, we know what we have to do is look at that r, we'd square it, okay, because it would be r times r, cis, and then in here, because we'd be adding the two thetas together, we'd have theta plus theta, and you can also write theta plus theta as 2 theta. So for a z, that's just another thing that you might find if you have a z and you want to square it. Okay, it's just a very useful way of looking at things. The other thing that I've got down here is the geometrical significance of complex number multiplication. And basically it just shows you what happens if you have a complex number z1 with its angle theta 1, and if you had another complex angle, it's not shown here, but you'd have a z2, and here theta 2 is a bit bigger, okay, and it had its own length r2. z1 times z2 is actually moved around the angle of z1 plus the angle of z2, so that's why you've got this movement here, okay, so the multiplied complex number is over this way, and the length of that new complex number, this isn't really to scale I guess, but it would be much bigger than these two because you're multiplying the two lengths together. So on the next page we've got division of complex numbers, and there's just a little proof here for that. So two complex numbers of the form r1 cis theta 1 and z2 equals r2 cis theta 2. If you're dividing them one by the other, you can see that you've got the proof here that when you're dividing complex numbers, it's the two moduluses now divided by each other, and this time instead of multiplying the angles, you subtract them. So it's kind of going to end up being an opposite version of this. So you'd be going back the other way, subtracting one angle from the other, and your divided complex number will become shorter because you've got a division for those moduluses. And there's some other properties here that are interesting that we get from this result. But this is the key result. on division. So the key results that we're interested here for multiplication and division is that if you have two complex numbers, z1 equals r1 cis theta 1 and z2 equals r2 cis theta 2, that if you're dividing or multiplying, if you're multiplying the complex numbers, you're going to have r1, r2, multiply the moduluses together, cis, and we add the angles together. So multiplying is adding. If we divide those complex numbers, we divide their moduluses and we subtract, whichever one is on the top, we subtract the one that's underneath its angle. So they're the two key formulas that you want to get out of this one for multiplying and dividing complex numbers.